Namaste everyone. I am Krish Jasani and today me and my group are going to explain some of the topics from the gravitation chapter. Firstly, Sneh will be explaining and deriving the equation for the maximum height attained by a projectile under gravity.
Maximum height attained by a projectile. On the basis of gravitational potential energy, we can determine the maximum height attained by the body projected upward with a certain velocity or the velocity of the projectile required by a body to reach a certain height. Derivation of maximum height attained by the projectile. We can derive the maximum height by using the formula of energy conversion, which is Ki plus Ui equals Kf plus Uf, where K stands for kinetic energy and U stands for gravitational potential energy. In the first step, we will substitute the values of K and U, which is half mv square and minus gm m upon r. In the gravitational potential energy, G stands for the gravitational constant, lowercase m stands for the mass of the projected body, R stands for the radius of Earth, and uppercase M stands for the mass of Earth. In the next step, we will change the sides of the term to make the equation positive. Also in this step, M will be subtracted, hence we are left with Gm upon R plus H equals Gm upon R minus V square upon 2. In the next step, making R plus H as the subject, hence we are left with Gm whole upon Gm upon R minus V square upon 2. In the next step, making H as the subject and taking LCM, finally you get H equals V square into R whole upon 2 Gm upon R minus V square.
Now I will be explaining the concept of escape energy and escape velocity and deriving the equation for the same. Escape velocity is the velocity that is sufficient for a body to escape from a gravitational center of attraction without undergoing any further acceleration. Next, the features of escape velocity are as follows. It is independent of the mass of the body and its angle of projection from the surface of the earth or the planet. The value of escape velocity depends upon the mass and the radius of the earth or the planet from the surface of which the body is to be projected. So the escape velocity will be different for different planets. If a body is projected from earth or planet with velocity v dash such that v dash is smaller than the escape velocity, then after reaching a certain height, either the body will move in an orbit around the earth or the planet, or it will fall back to the planet. If the velocity of the projection of the body from the surface of the planet is greater than the escape velocity of the planet, then the body will escape out of the gravitational field of that planet and it will move in interstellar space. Here is a picture showing escape velocities of different planets. Now the formula for escape velocity is under root of 2 gm by r, and its derivation is as follows. Let a body move from Earth's surface to infinity. So its initial potential energy would be minus g m1 m2 by ri, and its initial kinetic energy would be half mve square. Thus the total energy would be the sum of the kinetic and potential energy of the body on the Earth's surface. It is half mve square minus g m1 m2 by ri. Now when the body is at infinity, its potential energy would be minus g m1 m2 divided by r infinity, where r infinity is the infinite separation between the center of the earth and the infinite point. And as the value of r infinity is very large due to its infinite distance, the potential energy of the body at infinity is equal to 0. Similarly, the kinetic energy of the body at infinity would be equal to half m v infinity square, which in turn is equal to 0 because the velocity of the body at infinity is equal to 0. Therefore, the total energy of the body at infinite point would be equal to 0, as the kinetic energy and the potential energy of the body at infinity is equal to 0. Now, according to the law of conservation of energy, the total energy remains constant for a closed system. So, in this scenario, the closed system contains the two bodies with the gravitational pull between each other. Moreover, no outside force or energy is acting on any of the masses. Therefore, the total energy of the body on the Earth's surface is equal to the total energy of the body at infinity. Therefore, the sum of the kinetic and potential energy of the body on the Earth's surface is equal to the sum of the kinetic and potential energy of the body at infinity. And by substituting the values, we get that half mve square minus gm1 m2 divided by ri is equal to 0. And by adding gm1 m2 divided by ri on both sides, we get that half mve square is equals to gm1 m2 divided by ri. Therefore, when we make ve as the subject, we get the equation of the escape velocity, that is, escape velocity is equals to under root of 2 gm by ri. Next, we have the consequences of escape velocity. There are mainly two consequences of escape velocity, which are as follows. First one, the absence of atmosphere on the moon. On the surface of the moon and during its regular temperature, the velocity of the gas molecules is greater than that of the escape velocity of the moon, and so they escape its gravitational field, resulting in absence of atmosphere. Second, the black hole. These are objects or areas in space having very high density, so that escape velocity from these objects become greater than or equal to the speed of light. Thus, even the light particles cannot escape out of it, leading to a dark space. If light is sent to such objects, nothing will return back, forming black holes. Lastly, we have escape energy, which is the kinetic energy given to a body to project it with the escape velocity. Its formula is gm1 m2 by r equal to the maximum potential energy. So, if such amount of energy is supplied to it, then the body will attain its escape velocity and move towards space. Thank you. Now Rushin will be explaining about geostationary and polar satellites.
Hello everyone. Let's begin with geostationary and polar satellites. So first of all, we will talk about geostationary satellites. So let's begin. Geostationary satellites are the satellites whose period of revolution is same as that of Earth, which is 24 hours. And due to the same period of revolution like that of Earth, it would appear stationary over a point on Earth's equator. Such satellites are known as geostationary satellites. So let's talk about the conditions necessary to be a geostationary satellite. First, the angular velocity of the satellite should be same as that of Earth, and the direction of its rotation must be counterclockwise, which is from west to east. Last one we have is that satellites should rotate in an equatorial plane. Here, equatorial plane means a plane passing through the equator of the Earth. So the next subtopic we have is uses of geostationary satellites. These types of satellites are used for tracking volcano ash, land temperature, vegetation coverage, and much more. Next topic here is polar satellites. These are specific type of satellites having comparatively much smaller altitude, which is around 500 to 800 kilometers. These satellites orbit the poles of the Earth in north and south direction. Due to the orbit of the satellite, it can scan the whole Earth in terms of strip. Adjacent strips are viewed to see the whole image of the Earth. Strips are taken due to the rotation of the Earth. The time period of these satellites may vary from 2 to 6 hours. The last subtopic here is uses of polar satellites. These satellites are used for monitoring weather, military operation, spying, mapping of the Earth, etc. Thank you everyone for your attention.